Hello everyone, this is Reza Wazi, and in this short lecture you are going to learn about data mining validation. Validation is also known as model performance measurement because at the end I'll give you some sort of measurement or a means or a tool for you to evaluate how good your model performed. It is also meaningful in the context of predictive analytics. In the context of descriptive analytics, you may have some indirect ways to measure how good your model performance is. For example, look at the clustering analysis. This type of validation or this type of model performance measurement that you are going to learn in this lecture are not going to be applicable to something like clustering or to something like correlation or to any other sort of descriptive analysis such as association rules analysis. This concept of validation or model performance applies directly to predictive models. And basically, you want to figure out how accurate your predictions are. And in almost all of validation tasks, you are trying to divide your old or your past dataset or the dataset that you call training dataset into different parts. You use some parts or one big part as your training sample, and you remove the target variable from the other parts and use them as your scoring sample. The logic is that you already know the results, you already know the values for the target variable that you are trying to predict in your scoring sample. Remember, the scoring sample is a part of training sample or used to be a part of training sample. So you actually know those values, you know what the values are in reality. You can construct your model on the first part and then apply it on the second part and see how your predictions are different from the actual values, and then come up with some sort of understanding of how accurate your predictions are. In validation, you can have something like a simple split that you split your training data into two parts of training and testing. And remember, the second part is not called scoring anymore. I use scoring because you're already familiar with the concept of what scoring is. In the context of validation, we call them training and testing. So in the simple split validation, you are going to simply divide your training into two parts, training and testing. And then you can go 50-50, you can go 40-60, you can go 70-30, depending what would be a good reasonable minimum number of observation for your training model that you want to have in your training. So deciding on the training portion and testing portion partly depends on what type of methodology you are using. And then it's cross validation. Cross validation, which I personally prefer over simple split, will divide your data, your training data, into k parts, and you will define the k. K can be 2, k can be 10, k can be 20. It divides to k parts that this k is user defined, and then it uses k minus 1 parts for training and 1 part for testing. It'll calculate the results and they'll move next. It will use again that one testing part plus k minus 2 other parts, and we'll construct the model and we'll use on one remaining part. It will continue this until all these parts are used as testing, and then we'll give you an aggregated reading of the performance measurement. Now, to get a better understanding of the validation process, let's consider a classification case. In this case, you have a data set of 1,000 people that are showing certain symptoms of an illness. You know that whether they've been infected by a certain virus or they have not. So you know that whether these symptoms are a result of that certain virus or not. And remember, this is the training sample, so you already have the test results and you already know that 150 of these individuals, they have the virus, and 850 of them did not have the virus, they just had the similar symptoms. Now let's consider few concepts here. You have true negative. True negative are the cases that were negative and predicted negative. You have true positive, cases that were positive and predicted positive. False negative are cases that were positive, they actually had the virus, but they were predicted negative. And false positive were cases that actually were negative, but they were predicted positive. Now let's see how we can use these concepts and come up with accuracy measures. Now let's put the concepts that we learned in the previous slide into action and understand two new concepts, which are called precision and recall. You use the previous dataset, the training dataset, and you created your model, and now you want to validate your model using either split validation or cross validation. The model results came out, and you know that the model predicted 200 of those cases to be positive and 800 of them to be negative, while you know that in reality only 150 of them were positive and 850 were negative. So here you have some inaccuracies. Let's go ahead and see how we can calculate precision and recall. Look at this table. On the columns we have true readings, true positive, and true negative. So if you add up the numbers in the columns, they have to amount, or they have to be equal to the true number of positives. We have 150 positives, so it's 120 plus 30. It is going to be 150. We have 850 negatives, so if you add 80 and 77, then I'll be equal to 850. And now look at the rows. We have predicted positive. Our model predicted 200 cases to be positive. So if you add up the number in the rows, it's 120 and 80. It'll be equal to, and our model predicted 800 cases to be negative. Again, if you look at the row, it'll be 30 plus 770. It'll be equal to. Now let's consider true positive and false positive numbers. So you know that our model predicted 200 cases as positive. Now when we go ahead and compare these results to what actually happened, we understand that only 120 of these cases were true positive. The rest, 80 of them were false positive. It means that they were predicted positive, but they were actually negative. They were true negatives. Now, if you look at the negative predictions, you can see that 30 of them were false negative. It means that they were predicted negative, but they were actually positive. They were true positives, but predicted negative. That's why you see false negative as 30 there. And you can see that 770 of the subjects were actually true negative. Now, let's consider precision and recall, how we can calculate precision and recall using this knowledge. Precision is a proportion that you can calculate using predicted correctly, or the number of cases that were predicted correctly divided by the total number of prediction. So what would be the precision for predicted positive and predicted negative? Let's go ahead and calculate the precision for predicted positive. We have 120 that were predicted correctly divided by the total number of prediction. What is the total number of predictions for positive? It was 200, so it's going to be 120 divided by 200. You can calculate precision for predicted negative as well. You would understand how precise your predictions were. So that would be predicted correctly divided by the total number of predictions. The total number of predictions for negative cases were 800, and predicted correctly for negative cases were 770. So it will be 770 divided by 800. So precision refers to how precise your predictions are. Then now let's go ahead and consider recall. Recall is predicted correctly, cases that are predicted correctly divided by the total number of corrects. Here the total number of corrects are the total actual number of corrects. And recall tells you about the proportion of the cases that your model were actually able to capture. So here the recall for positive cases would be 120, which was predicted correctly, by the divided by the total number of corrects. What was the total number of actual positives? 150. So it will be 120 divided by 150. And then you have predicted correctly divided by number of corrects for the negative cases. That would be 770 divided by 850. Now let's take a look at this table. It's essentially the same table as the previous slide. I just added the class precision and class recall measures. Let's look at the class precision. For positive cases, it tells you what percentage of positive predictions were correct. You know that 120 out of 200 or 60% were correct. For negative cases, again, look at the negative cases. It tells you what percent of negative predictions were correct. You know 770 out of 800 were correct. So class precision tells you, or the precision measure tells you what percentage of each case that you had were correct, or how your algorithm or how your methodology were correct in prediction of each cases. And on this one, you could see that your algorithm, your data mining methodology did much better in predicting negative cases as opposed to positive cases, since the precision was 60% for positive cases and 95% for negative cases. On the other hand, what does recall tell you? Recall refers to what percentage of each case you could catch through your algorithm. So here, look at 120 divided by 150. It tells you what percentage of positive cases that were in your dataset you could actually catch using this methodology. You could actually catch 120 out of that 150, right? So it's 80%. You could catch those cases, those positive cases, at 80% rate. Now look at the recall for the negative. It tells you about the percentage of negative cases that you could catch. Here you caught 770 out of 850 possible cases. So your recall would be around 90%. And can you tell me about the accuracy of your model? How accurate your model was in general? Because class precision and class recall will give you readings for each class, for each classification that you have in your dataset. Right now our dataset, our target variable, had only two classifications. It was a binary, positive or negative. You could be using different cases. You could be having a target variable that has 5 different categories or 6 different categories. So in that case, you would have had 5 or 6 columns and rows, and 5 or 6 class precision and recall. You would have 1 class precision and 1 class recall per number of classes or categories that you have in your target variable. Now, going back to accuracy, what do you think is the overall accuracy of your model? Look at the positives, the number of positives that you could actually catch, and the number of negatives that you could actually catch. You could catch 120 of positives and 770 of the negatives. So these were your correct catches, these were your correct hits. So if you add them up, they will be close to 890. They will actually be 890, right? And how many cases you had? You had 1,000 cases. So if you divide 890 by 1,000, you will get your accuracy rating, which is 89%. So here on this slide, you have what we just went through in the previous slide. Starting with accuracy. Again, what is accuracy? It's the percentage of your predictions that were correct. So you know that you could identify 120 of the positive cases correctly using your model and 770 of the negative cases. So if you add them up, you will have 890, and if you divide that by the total number of observations, you will get your accuracy readout. Then you have your precisions and recall. So precision tells you what percentage of the predictions were correct for each case. So you will have one precision reading for each category or each case that you have in your target variable. Here in this case, we only had two categories, so we have two precision readings, one for positive cases, one for negative cases. So here the precision reading for positive predictions is 120 out of 200, because you were only correct in 120 of the cases out of the 200 you predicted. So you were only correct in 60% of the times, or your model was correct in 60% of the times when it comes to positive cases. However, when it comes to negative cases, your model could predict with 95% precision. And how you calculate that? Was the number of true negatives divided by the number of predicted negative cases, which is 800. There is a typo. That should not be 810. That should be 800. So it's 77 out of 800, which should be close to 95%. So on this specific case, your model did much better in predicting negative cases compared to positive cases. So one reason for this high precision for negative cases goes back to your dataset, the nature of your dataset. In your dataset, you had 850 negative cases and only 150 positive cases. Think about it. If you had a model that would go ahead and predicted all cases as negative, you would still get 85% precision for negative cases. Why? Because 85% of your population, 85% of your observations are negative. So if your model was going to predict all the cases as negative, you would still get some good readings for precision as it comes to predicting negative cases. Now look at positive cases. So your model predicted 200 observations as positive, which you know that only 120 of them were correct. So the precision for positive cases were only 60%. If you were going to predict something as positive, that means that the chances for you to be correct, it would have been 60%. Now look at the recall. Recall refers to the percentage of each case or each category that you could actually catch. Here, for positive cases, you know that you actually had 150 positive cases in your population. You could catch 120 of them. So that's 80%. And for negative cases, you had 850 and your model could catch 770 of them. That's close to 90%, 90% and a half. So how can we interpret these accuracy, precision, and recall? It's not a very easy job to interpret these. You need to know the goal of your analysis. Accuracy will always give you some overall measure, some overall goodness of your model. The higher obviously the better. But what really matters is precision and recall, and they're tied to your analysis goal, to what you want to achieve. Let me give you different scenarios here. So one scenario is like this, that what if you were going to spend a lot of money on those cases that were predicted positive, right? To cure them, or maybe to get to the bottom of their results, their illness, to figure out if they're really sick or not. So this model predicted 200 of them to be positive, and only 120 of them turned out to be actual or true positives. So only correct 60% of the time. It means that you will be wasting a lot of money. But at the same time, if the negative cases were important for you, if you were spending money on the negative cases instead of positive cases, then this precision would have been good for you, because it's 95%. You were correct, your predictions were correct about negatives at 95%. So it justifies this analysis, it justifies this approach and this modeling. So again, if the positives are important for you, and if you are spending a lot of money on the subjects based on the positive predictions, the positive predictions does not look good. There's 40% error in positive predictions. And if you were spending money based on the negative predictions, if the negative predictions or the case of negative is very important for you, then this model is a pretty good one. It's 95% precise in predicting negative cases. Now look at the recall. Now let's change the scenario. What if now the scenario is to make sure that people who have this virus and come to our country will catch them and we do not let them out of quarantine? Then this model can actually catch 120 out of 150, which is 80%. That is not utterly bad. So it means that you could catch 80% of already existing positives. That's not a bad thing. You may want to rely on this. And what percentage of negative cases did you catch? You could catch 90% of the negative cases. That's not bad either. So again, depending on the goal of your analysis and which of these categories are really important for you and why it is important for you, it is like a cost saving, it is money spending, what is the goal of analysis, which category is more important for you, then your interpretation of these precision and recall would be different. So you will use accuracy as a general measure, as to give you some general understanding of how good your model is doing, and you will focus on precision and recall, and you interpret precision and recall for each of your cases. You have 2, 3, 4, 5 cases. You interpret the precision and recall readings based on the goal of your analysis and based on your business goal or your organization goal, what you want to achieve. If your goal is to achieve or to accurately predict negative cases, then this model is golden for you. If your goal is to better predict positive cases, then this is not a really good model, even though you get a 90%, almost 90% accuracy. The accuracy for positive cases or precision for positive cases is only 60%. You probably have figured it out by now, or you may have questioned. Precision, recall, and accuracy, they apply to classification problems. They are only useful if you have a discrete or categorical target variable. What if you have a continuous target variable? Then you cannot really use accuracy, precision, and recall measures because you do not have classifications. You have a continuum. Most of regression analysis cases are of this sort, you have a continuous target. So when you are dealing with continuous target, or when you are dealing with some sort of regression modeling, regression prediction, then the performance measures will change from accuracy, precision, and recall to something else. For regression models, there is something called R squared. There is a measure called R squared, and it's a measure of model fit. The higher the R squared, the better the model. It actually tells you about the proportion of variation in the target variable that is explained by your regression model. So the higher the R squared, the higher that proportion of variation, and the better your model. Here's the one exception. R squares above 0.9 are always questionable. When you get an R square that is above 0.9 or even above 0.85, you always have to go ahead and look for problems of multicollinearity, problems of high correlation among your independent variables. Remember that regression has a basic assumption, and that assumption is the independence among your independent variables. But when your independent variables are not totally independent from each other, they are correlated with each other, you will run into problem of multicollinearity, which generally will go ahead and inflate your R square. So not always high R squares are desirable. They are generally good, but once you get a really good R square, something 0.85 or 0.9 and above, you have to go ahead and consider if all the assumptions of regression are met, or some of them are violated, and if so, what you can do with it. Another measure when it comes to continuous target variable and regression cases, or any other methodology that uses continuous target variable, is called RMSE, or root mean squared error. The root mean square error is the square root of the average of the square of all errors. And what is error in the regression case? The error is the difference between your predicted value and your actual value. That's what you call an error. So you'll go ahead and add all those errors and average them, and then take the square root of them. That will be your RMSE. And as I said, it can be used on regression cases, and it can be used for evaluating on other modeling methodologies that use a continuous target variable. One thing about RMSE that you need to pay attention to is that it is scale dependent. And what do I mean by scale dependent? It means that there is no absolute good or bad threshold, and it depends on the scale of your dependent variable or your target variable. For a dependent variable which ranges from 0 to 1000, an RMSE of 0.7 is a small one, is a significantly small one. It's really good. It shows you do not have much error in your system. But if the range for your target variable was from 0 to 1 instead of 0 to 1000, then the same RMSE reading, 0.7, wouldn't be good, because now you are dealing with a much smaller scale, and 0.7 is 70% of your scale. So in general, the smaller the RMSE, the better. It means you have less error. But you have to interpret that reading in the light of the scale of your dependent variable or your target variable. Okay, this concludes the lecture on model performance measurement or model validation.